Salam, peace be upon you. My name is Muhammad Laif Siddiqui, the father of holophase. We began by showing that pattern comes first. Phi is the root permission for distinction. Because phi is circular, only relations are public. We then built local reading, finite windows, boundaries, stitching, and finally reached the global truth. Patterns can carry memory around loops. Phi pattern science, the complete foundation. Part 14, the topological face of phi pattern. Winding, holonomy, and global memory. There comes a moment in any serious journey of understanding when you realize that looking nearby is not enough. Until now, we have learned how to read a pattern locally. We learned that pattern is primary. We learned that phi is not a thing, but the primitive permission for difference. We learned that phi is circle-valued, so no absolute zero is public. We learned that only relations can be certified. We learned to read local difference, to unwrap locally with lifts, to track local change through the first carrier, spoken aloud as A equals D phi tilde, and to describe local signatures through jets, always with the humility that our read depth is finite. We then learned that time, space, and motion are not primitive containers, but readouts of one differentiated pattern. We learned that pattern language has lawful regions and unlawful ones. We learned to mark excisions, to fear aliasing, to declare boundaries, and to stitch many local charts into one global atlas. Now another door opens. Even after all that, something still remains unseen. A pattern can be perfectly smooth in every local patch you inspect. It can look ordinary everywhere nearby. Every derivative can behave. Every chart can seem clean. Every little neighborhood can appear harmless. And still, the pattern as a whole may carry a deep fact that no local inspection can reveal. That deep fact is topology. Topology is the memory a pattern carries when you go around and come back. It is what the pattern remembers globally, even when locally everything looks innocent. This part is the story of that memory. The first hint: coming back is not always simple. Imagine you take a walk around your neighborhood. You leave your front door, turn left again, loop around the block, and come back home. You return to the same place, so it feels natural to think that nothing deep has happened. You started here, you ended here, end of story. But now imagine a different path. Imagine you are walking up a spiral staircase inside a tower. You begin facing north on the ground floor. You walk in a circle and come back to the same direction around the tower, but now you are one floor higher. You returned in one sense, but not in another. The loop carried memory. Or imagine walking on a mountain trail around a peak. From one small section of the trail, nothing seems unusual. But after you complete the loop, you realize the whole route encircled something. The meaning of the path was not in any step by itself. It was in the closed journey. This is the first intuition of topology. A closed path can reveal something that no point on the path reveals by itself. That something is not local detail, it is global structure. Why local smoothness is not the whole story. Up to this point, we have focused on local readability. Local reading asks questions like this: what is changing here? How fast is it changing? How is the trait itself changing? What local signature can be read in this window? These are good questions, necessary questions, but they are not enough. Why not? Because local derivatives tell you how a pattern behaves nearby, not how the whole pattern is tied together. A small patch of a cylinder and a small patch of a flat sheet can look similar, A small patch of a Mobius strip and a small patch of an ordinary band can look similar. A small neighborhood inside the vortex and a small neighborhood inside the calm rotating flow may look similar. The deep difference appears only when you move through the whole structure and try to return. So, the first great lesson of topology is this: a pattern is not exhausted by what it does locally. A pattern may carry whole pattern information that cannot be reduced to local smoothness. That is why topology is not an advanced decoration placed on top of pattern science. It is part of pattern identity itself. The circle changes everything. To understand why topology appears so naturally here, we must remember something fundamental. Phi takes values on a circle. This means that phi is not like a line with a permanent beginning and end. It is like an angle, it wraps. If you move continuously along a path, the value of phi can change smoothly. But because the value space is circular, going far enough can bring you back to a value that is equivalent to where you began, except for whole turns around the circle. This is the heart of the matter. If phi lived on an ordinary line, closure would not naturally produce whole turn counts. But because phi lives on a circle, loops can accumulate full turns, and full turns can be counted. That count is not something we inserted by hand, it is something the pattern gives us. So now we arrive at one of the most beautiful ideas in the whole framework. Discreteness can emerge from continuity through closure. Nothing had to jump. Nothing had to be made digital by decree. The value changed continuously. But because the value space is circular and the path closed on itself, the total change around the loop had to come back to where it started, up to whole turns. Whole turns create integers. This is how the continuous gives birth to the discrete. The idea of winding. Let us now name the first great topological invariant, winding. Suppose you walk around a closed loop in the domain where the pattern is lawfully readable. As you move, the value of phi moves around its circle of possible values. Maybe it does not go all the way around. Maybe it goes halfway and comes back. Then the loop has no full winding. But maybe, as you complete your physical loop, the value of phi completes one full turn around its own circle. Then the pattern has winding number plus 1. If the value goes around twice, the winding number is plus 2. If it goes once in the opposite direction, the winding number is minus 1. In spoken form, the key relation is the total change of phi around a closed loop equals 2 pi times an integer. Say it slowly. The total change of phi around a closed loop equals 2 pi times an integer. That integer is the winding number. It counts how many whole times the pattern value wraps around its circle as you go once around the loop. This is already a stunning fact. No single point knows this number. No local derivative at one point knows it completely. You must go around the whole loop. Winding is whole pattern memory. A simple image, the ribbon around a pole. Imagine tying a ribbon around a pole. Wrap it once around and tie it. That is one winding. Wrap it twice. That is two windings. From one small piece of ribbon, you cannot tell whether it belongs to a single wrap or a double wrap. That local piece looks the same either way. The difference is global. You have to follow the ribbon all the way around. Topology is like that. A local patch does not tell you the global wrap count. The loop does. Another image, the clock hand. Think of a clock hand going around the dial. The hand moves continuously. There is no jump as it passes 12. But if you track how many full revolutions it makes, you get a discrete count. 1 turn, 2 turns, 10 turns. The count is not visible in the hand's local angle at one moment. At 12 o'clock, the hand can look exactly the same after one turn or after 20 turns. The local look is identical. The global memory differs. That is topology again. The local state can repeat. The history carried around loops can still differ. Holonomy, the more general memory of a loop. Winding is the simplest example of loop memory. Holonomy is the broader idea. Holonomy means, after moving around a closed path, what residue remains? What memory has the pattern retained from the journey? Sometimes that residue is exactly the winding number. But holonomy can be broader than winding. For example, a phase shift can remain after a loop. An orientation can return rotated. A direction can come back twisted. A transported frame can return altered. The broad lesson is simple. A closed loop can carry memory. Not memory in the human psychological sense, not memory as storage in a brain, but memory as a residue that survives traversal. You go around and come back, yet the return is not trivial. Something about the path matters. Something about the whole matters. That is holonomy. If winding is, how many times did we turn around the value circle? Holonomy is, what did the pattern remember about the closed trip? The mountain path and the compass. Imagine walking around the mountain while carrying a compass arrow painted on a board. Suppose the ground is curved, and the way you carry the arrow obeys a strict rule. Keep it as unchanged as possible relative to the path. When you return to where you started, the arrow may no longer point in the same direction you began with. You are back at the same place, but the transported direction has changed. That change is loop memory. It is not visible in any one step. It appears only after the whole loop closes. This is a good everyday doorway into holonomy. The loop as a whole can leave a residue. Why topology is not optional mathematics? At this stage, some people are tempted to think, this sounds like advanced mathematics, interesting, but perhaps not foundational. That temptation must be blocked. Topology is not added later as decoration. Topology follows directly from four things we already accepted. Phi is circle valued. Local descriptions require lifts. Global patterns are stitched from charts. Closed paths can be legally traversed in the atlas. Once those are granted, topological questions become unavoidable. You must ask, does the value wind around the circle? Do chart transitions close consistently? Does the loop remember something global? Can the whole pattern be globally unwrapped or not? These are not luxuries. They are identity questions. Two patterns can be locally identical in every patch and still differ topologically. If you ignore topology, you can misidentify the pattern. So topology belongs to the what it is of the pattern, not merely to the how we choose to describe it. Local sameness can hide global difference. This is one of the deepest truths in the entire framework. Two patterns may agree locally everywhere and still differ globally. Imagine two roads painted with arrows. In every small neighborhood, the arrow pattern looks the same. Same density, same smoothness, same local turn rate. But on one road network, following the arrows around a full loop returns you with no residue. On the other, following them around a full loop accumulates one full turn. Locally, they match. Globally, they differ. This means no amount of purely local checking can guarantee global identity. That is why topology is needed. It protects us from a very dangerous mistake. The mistake of thinking that local agreement automatically implies global sameness. It does not. The Mobius strip as a teacher. A Mobius strip remains one of the best teachers here. Take a paper strip, twist one end by half a turn, then join the ends. Now trace a line along the center of the strip without lifting your pen. What happens? You eventually return to where you started, but only after traversing what seemed like both sides. In fact, there is only one side. No local patch warned you of this. Every little patch looked ordinary. The surprise was global. The strip carried a hidden whole pattern truth. That is topology. The pattern is not merely what every small part looks like, it is also how the parts are globally joined. Loops must be legal. Before we make any topological claim, we must respect the discipline already installed earlier. Not every path is lawful. A loop used for winding or holonomy must satisfy the legality requirements of the atlas. That means it must lie inside the appropriate domain, it must not cross excised regions without declared lawful handling, it must respect branch cut declarations, it must use orientation conventions consistently if those matter. Why is this important? Because illegal loops can fabricate false topology. If you drag a loop through a region where the language itself breaks down, then whatever winding you calculate may be counterfeit. So topology is not wild mysticism. It is disciplined global accounting. The loop has to be legal before its memory can be certified. The branch cut warning. Remember local lifts. A lift is a lawful local unwrapping of phi into a line-like representative, spoken as phi tilde. But lifts are not unique, and branch cuts are declared seams where global unwrapping fails. When doing topological work, branch cuts matter. Why? Because if you ignore them, you may accidentally erase or invent winding. A branch cut is not a defect in the science, it is an honesty device. It marks where one representation cannot remain globally smooth without a jump. So a rigorous topological claim must not hide branch cut dependence. It must declare how the loop and the chosen local descriptions relate. Again, the lesson is simple. Global memory requires disciplined bookkeeping. The birth of integers. Now let us linger a little longer on the miracle at the heart of this part. A pattern value changes continuously. A loop closes continuously. The value space is circular. From these three facts, integers appear. Not because we inserted counting into the world, not because we decided that nature likes whole numbers, but because closure forces return modulo full turns. Continuity plus circularity plus closure gives total loop change equals 2 pi times integer n. That integer is born from the structure of return. This is one of the deepest philosophical beauties of the framework. The discrete is not always primitive. Sometimes the discrete is what the continuous leaves behind when the path closes. That idea reaches far beyond mathematics. It tells us how wholes can create counts, how cycles can create number, how repetition can leave stable residues. Everyday life examples of global memory. The idea may seem abstract, so let us widen it into ordinary life. The weekly routine. A person's day may look ordinary locally. Wake up, work, eat, sleep. But if you follow the full weekly loop, a larger pattern appears. Workdays, weekend, reset, return. The week carries a loop memory not visible in one afternoon. A family tradition. Any single family dinner may look simple, but the yearly repetition of a holiday meal carries memory. The pattern is not in one dinner, it is in the return. The loop stores meaning. A relationship. A conversation by itself may not reveal much, but the same conflict revisited over months reveals a winding pattern, the loop the relationship keeps carrying. The memory is global to the relational cycle, not local to one sentence. These are analogies, not exact topological proofs, but they help ordinary intuition. The whole loop can contain truth that no moment reveals. Topology across scales of the universe. Now let us walk across scales. At the quantum scale, phase around the loop can leave residues. Quantum systems can carry loop memory as phase holonomy. What matters is not only local amplitude, but the global path history. At the atomic and condensed matter scale, vortices, quantized circulation, and topological defects show that loops can detect stable whole pattern quantities invisible locally. At the biological scale, DNA supercoiling, circular metabolic cycles, and anatomical twists all remind us that organisms are not only locally structured, but globally wrapped and constrained. At the ecological scale, migration loops, nutrient cycles, and seasonal return patterns carry memory that is not in any single moment of the system. At the planetary scale, weather vortices, magnetic field circulation, orbital closure, and season cycles all express whole pattern residues of return. At the cosmic scale, rotation, field structure, and large-scale topological organization may carry global memory beyond local observations. At every scale, the same lesson returns. What the whole does around closure matters. Topology as identity content. So, what exactly does this part install? It installs the doctrine that topological invariants belong to pattern identity. If you ask, what pattern is this? The answer is incomplete unless it includes its lawful global memory content. That may include winding number, holonomy class, orientation structure, loop residues, non-trivial global stitching behavior. A pattern without winding is not the same as a pattern with winding, even if every local patch seems alike. A pattern with one twist is not the same as one with none. A pattern whose loops carry residue is not the same as one whose loops close trivially. These are differences in what the pattern is. The rigor layer. Now let us state the discipline clearly. The loop legality gate. Any topological claim must declare the loops being used and show they are lawful within the relevant domains. The topological invariability gate. Any claimed winding or holonomy must be shown to survive allowed representation changes and to be calculated with declared conventions. What must be declared? The loop set, the legal domain of traversal, excisions avoided or handled, branch cut conventions if material, orientation convention if material, the calculation or reasoning that yields the invariant. Why so much discipline? Because global claims are powerful. Powerful claims require clean accounting. The main firewalls. To protect this part from corruption, we installed several firewalls. No local-only proof of global identity. You cannot certify global sameness from local agreement alone. No illegal loops. A loop that crosses an excised or undefined region without lawful handling cannot support certification. No hidden orientation conventions. Clockwise and counterclockwise matter. Declare the convention when needed. No hidden branch cut dependence. If a result depends on how local lifts are glued, that glue must be declared. No reducing topology to optional decoration. Topology is constitutive identity content, not advanced ornament. What this part gives the framework. By the end of part 14, several major things become possible. First, we now understand that patterns remember globally. Second, we now understand how integers can emerge from continuity through closure. Third, we now understand why local readings and jets, though essential, do not exhaust pattern identity. Fourth, we now have the conceptual foundation for defects. Because one's loops can carry non-trivial memory, irreducible abstractions become possible. Places where the stitching cannot be globally flattened will no longer look like accidents. They will appear as real pattern features. This is the bridge to the next part. Refusal conditions. A topological claim must be refused if the loop is undefined, the loop is illegal in the declared domain, excisions are ignored, orientation conventions are hidden when material, branch cut dependence is hidden, atlas compatibility is unresolved. A global identity claim is made from merely local data. Refusal is not weakness. It is protection against counterfeit global claims. Final image, the pattern that remembers. Let us end with the simplest image. Imagine drawing a circle on the ground and walking around the tree at its center while holding a ribbon connected to the tree. When you finish one loop, the ribbon has wrapped once. Walk again, it wraps twice. At any single moment, the ribbon near your hand looks ordinary, but the whole walk leaves a count in the world. That count is not in one step, it is in the closed return. Topology is that count. Topology is the world's way of remembering a loop. And part 14 tells us something profound. Reality is not only what changes nearby. Reality is also what survives the round trip. That is why topology belongs to the core of phi pattern science. Because a true science of pattern must not only ask, what is happening here? It must also ask, what does the whole remember when we return? Always, peace be upon you.